So, to recap on Lecture 9 material, in that lecture we began to take atoms and elements and put them together to form more complex structures or compounds. There are two different types of compounds. We have the ionic type, and then we have covalent or molecules. We looked at the different properties of those two. We looked at the different bonding descriptions between ionic and covalent compounds, and we looked at the different rules for naming those different compounds. So now in this lecture 10, we are going to continue talking about compounds, but we're going to have to actually take back out our calculators because now we're going to start using those chemical formula and compounds in mathematical operations. We'll be converting between grams, moles, and molecules, and even atoms. So we'll have to be taking out our calculators again. I have a different camera view because in this lecture I'll take the time and show you how to input large numbers into the calculator, so we don't have issues during our next midterm 2. All right, so lecture 10, we're again looking at chemical formula, and now instead of just looking at the weights of one atom or a mole of atoms that are on the periodic table, we're now going to be looking at the weights of whole molecules instead, so just a collection of bonded atoms. So, to remind you how we put together compounds from atoms, we're taking individual atoms and making either ionic or covalent bonds to make single compounds or single molecules. And, that's how we form those ionic compounds and covalent compounds. So, we're taking these individual atoms forming molecules or compounds. So, like in one of the previous lectures, our laboratory scales aren't sensitive enough to detect single atoms. They are also not capable of detecting single molecules because molecules or compounds are just made up of just, a handful of atoms. So we have to think about what units can we use that we can measure molecules and compounds on a laboratory scale in our own labs. So yeah, like remember when talking about atoms, we typically are talking about units in AMU, which is just a tiny, tiny fraction of a gram. So instead, we need to be working in molar or mole amounts of substance. And so we can be in the unit of grams. So if you remember back a couple chapters when we were talking about atoms and taking the numbers, the values off of the periodic table and getting molar mass, we still apply those same concepts, but now to compounds. So to calculate the weights of compounds, we're still using the same skills that we used from elements in that we use the weights on the periodic table to help us out. But now, when we look at a molecule, we're looking at a collection of atoms that have, subscripts associated with them. So to get the weight, the molecular weight of a compound, you need to first know the chemical formula and take note of the number of each atom. So you have to understand those subscripts. And then you also need the atomic weights of each of the atoms. And you just get that right off of the periodic table. So, for example, if we wanted the molecular weight of methane, which is CH4, this is a molecule, it's a covalent molecule. Essentially, you would just break down the chemical formula and you would add up, you would take the sum of all of the atomic weights of all of the atoms present in that chemical formula. So the molecular weight for the whole molecule would be the weight of one carbon atom, and then add the weight of 4 hydrogen atoms. So if you look on the periodic table, you'll see that the weight of carbon is 12.01 AMU, just one carbon atom. So we're just going to take one of those. And then we also have 4 hydrogens. So we take the weight of one hydrogen and multiply by 4. And if you add those up, all of that up, you'll get the summation of all the weights of those atoms, the carbon and the 4 hydrogens. And you'll get that the molecular weight of CH4 is 16.042 AMU. So this weight is the weight of one methane molecule, one CH4 molecule. So when I say molecular weight What I'm talking about is the weight of one molecule. I like to differentiate that because we're going to learn a different type of mass instead of one molecule. We're going to also look at a mole of molecules, kind of the same thing what we did in when looking at atoms and elements. So I just want to make that distinction right here, that the weight of one CH4 molecule is 16.042 AMU. So let's do another example, a little bit more complex. So the molecular weight of caffeine here, I give the chemical formula of caffeine. It's C8H10N4O2. So these subscripts are telling me all of the number of atoms of each of these specific elements. And then this is what the structure of caffeine looks like. So to get the molecular weight of caffeine, all we need to do is take the sum of each of the different elements and their specific numbers listed here. So usually how I like to do it is to do it by element by element. So I'll kind of like rewrite all of these elements in a list form and add it up. So if there's there's 8 carbons, there are 10 hydrogens, there are 4 nitrogens, and there are 2 oxygens. So since there's 8 carbons, I'm going to multiply 8 by the molar mass, the atomic weight of 1 carbon. And off the periodic table, that's 12.01 AMU. So 8 carbon atoms times the weight of 1 carbon atom, which is 12.01 AMU. The atomic weight of hydrogen is 1.008 AMU. The atomic weight of nitrogen is 14.01 AMU, and then oxygen is 16.00 AMU. All right, so I'm just going to, do essentially what I'm doing is the subscript for each of these atoms times the atomic weight of one of the atoms, and then I'm going to get all those numbers here, and then I'll just add it up, and that will give me the molecular weight of one molecule. So if I do these operations, so it's 96.08 AMU, that's how much all the carbons weigh. All the hydrogens weigh 10.08 AMU. All the nitrogens weigh 56.04 AMU. And then the oxygens all weigh 32.00. So if you add that all up, you'll get the weight of the whole molecule. So C8H10N4O2. And so that equals 194.20 AMU. So as long as you have the chemical formula and a periodic table, you can get the molecular weights of any molecule. So I already mentioned in that first slide that in lab, we don't have any instruments that can measure an AMU. We can't measure, tiny fractions of a gram. So we need to think of a different unit to measure quantities of matter in an amount that we can actually measure in lab. And so that brings us to molar mass. So we were just talking about molecular weight. This is the weight of one molecule versus molar mass is the weight of 1 mole's worth of that molecule. It's worth of molecule. And so remember, a mole equals 6.022 times 10 to the 23, in this case, molecules. All right. So in that previous slide, we got the weight of one caffeine molecule. We got that it was 194.2 AMU per molecule. So instead, what molar mass measures is the mass of the compound, all of the atomic masses when you have a mole's worth of molecules. So how much does 6.022 times 10 to the 23 molecules of caffeine weigh? Well, thankfully, the periodic table tells us this, and it's not that much different. Essentially, you calculate molar mass the same way we just did molecular weight. Molar mass is the same value, but molar mass has a different unit than molecular weight. Again, molecular weight only measures one molecule, while the molar mass is the mass of 1 mole worth of that molecule. So here, if we look at caffeine, the molecular weight that we just got was 194.2 AMU of one molecule. The molar mass of caffeine is 194.2 grams when you have 1 mole worth of caffeine. So if I had 6.022 times 10 to the 23 caffeine molecules, it would weigh 194.2 grams. So you see how the numbers are the same, but what's different here is the actual unit. That here we're talking about in molecular weight, we're talking about 1 molecule and we measure it in AMU versus molar mass is measured in grams, and that's when you have a mole's worth of that specific compound. So we can do the same thing for methane. We looked at methane, we calculated its molecular weight. 1 molecule of methane weighed 16.04 AMU versus the molar mass of methane. It's still 16.04, but it's grams per mole. So mole meaning when you have 6.022 times 10 to the 23 of that methane molecule. CH4 molecules. So you can see that in lab, we're much more likely to be using, weird, in lab, we'll be much more likely using molar mass because now we have a unit in grams, but now we have to be thinking and working with moles worth of substances. So let's do a practice problem where we use these new quantities that we just learned about. So how many grams does 5.31 times 10 to the 24 molecules of caffeine weigh? So I'll just kind of remind you guys how we're able to interconvert between different amounts of matter. We can talk about matter in terms of gram, or we can talk about them in terms of mole, or we can talk about them in terms of atoms, and now instead we're thinking about molecules, atoms, or molecules. So in order to convert between grams and moles, we use molar mass of either the compound or the element. So these are all skills that we learned in a previous lecture. And then to interconvert between moles of atoms and just single atoms, we use Avogadro's number. So we also use Avogadro's number to interconvert between moles of molecules and molecules themselves. So remember, Avogadro's number is just a counting number. So when we have 6.022 times 10 to the 23 caffeine molecules, that also means we have 1 mole's worth of caffeine molecules. So just keep this in mind whenever, because for example, this question is asking us to go from molecules. We want to go from molecules to grams. So you see, in order to get from this side to grams, we have to go through moles. So just keep that in mind. I'm going to move that somewhere else. I'm going to move that over here. Okay. So this question is, how many grams does all these molecules weigh? So they, thankfully, they give us the chemical formula of caffeine, and they also give us the molecular weight. But as a good chemist, you know that molecular weight in AMU is the same number, 194.20 grams per mole of caffeine. That if I have a mole's worth of caffeine, it will weigh 194.2 grams. The reason I'm writing it like this instead of using the molecular weight, I'm using molar mass instead of molecular weight, is because this question is asking for grams. And AMU is not a gram, it's a fraction of a gram. So I'm going to use the quantity that has grams in it. Right? So I see that they give us molecules. So if you revert back down to this guide here, if I want to go from molecules to moles, I have to use Avogadro's number. And then if I want to go from moles to grams, I use molar mass, which is right here. So I'll just rewrite all those conversion factors here, or qualities that I'll use. So I'll just rewrite molar mass that I just wrote here. So 194.20 grams per mole. That can be rewritten as 194.20 grams of caffeine equals 1 mole of caffeine. So I'm rewriting molar mass the same way I rewrote the equalities for molar masses of atoms, but just instead of talking about grams versus of an atom, I'm now talking about the grams of a whole molecule. So I rewrote that, and then the other conversion is Avogadro's number. 1 mole of something equals 6.022 times 10 to the 23 molecules or atoms. But in this case, because we're talking about molecules and molar masses of molecules, I'm going to use the conversion or the Avogadro's number with number of molecules. All right. So typically with any word problem, you start with the number that's given here. And so right here, you want to start with molecules. So I'll pick a different color. So I'm going to start with 5.31 times 10 to the 24 molecules of caffeine. I'll be super specific. All right, so right now this number is in units of molecules of caffeine. So you see here, if you remember our guide, we need to go from molecules to moles. So I will use Avogadro's number to do that, right? Because that's the thing that you use, and make sure that you canceled the units out. All right, so right now we're in molecules, so I'm going to put 6.022 times 10 to the 23 molecules in the bottom. And now we have 1 mole of caffeine up top. So now you see units cancel, and so I'm in moles of caffeine. So now I can use that other conversion factor that I've been saving. 1 mole of caffeine is equal to 194.2 grams. And so now I can use that conversion factor. So 1 mole on the bottom, 194.20 grams of caffeine up top. And then we can show units canceling. All right. And then that's our answer because it will be in the unit of grams of caffeine. So I'll just quickly show how I put this into my calculator because I know that there was a lot of issues with using the calculator and exponents on the on midterm 1. So I'm going to take extra time to show how to do that, how to input these exponents into your calculator. So I'm just going to blow myself up real quick so we can see. Okay, there I am. Move the camera. All right. So I'm gonna do this problem on this kind of calculator. I also have, if you stick around, I also have this calculator, and I'll do another problem with this one later. So how I do this in input exponents on a calculator is I use this EE button. This EE button essentially means, okay, so I'll write it here. EE essentially means times 10 to the number. So if I write like 5 EE, so I pressed EE and you see this like number comes up to the side, you can put like 2. So 5 times 10 to the 2 would be 500. So that EE is just telling the calculator, hey, put times 10 to the number, input the exponent number, and then, hit your operation and see how it says 500. Or, if I say 8 EE to the negative 1, so 8 times 10 to the negative 1 would be 0.8. And there it is, 0.8. So there's a little trick to use the calculator so you don't actually have to write times 10 to the exponent, whatever. So let's actually I'll show you how I input this question onto my calculator. All right, so sorry you can't see can you see? No. Okay. So hopefully you wrote down the expression here, but I'll show you how to put it in. So we start out with 5.31 times 10 to the 24 molecules. So I'm not going to write times 10 to the 24. I'm going to use this EE button and just hit 24. All right. And then we're going to multiply that by, just show it here. Whoops. Okay. We're taking that number and we are multiplying by 1 over 6.022. 022 times 10 to the 23, so that's Avogadro's number. So times 1, I don't have to do that, but divided by 6.022 times 10 to the 23. So I'm going to take that first number, hit divide by 6.022, and then since now we have an exponent, this is scientific notation, I'm going to click that EE button and say 23. I could hit equals. There's equals. All right? But I'm not quite done yet. I still have to do these screens around. Times the molar mass of caffeine. So times 194.20 equals, and there it is. There's our answer. So our answer here is 1712.4 grams of caffeine. All right, so that's how you input that in your calculator. All right, sorry, I just took a minute to adjust my screen. So after sticking in the calculator, we got 1,712 grams of caffeine. But let's take a look at our sig figs. The number given here only has 3 sig figs. Remember that the exponent does not contribute to, the exponent in scientific notation does not contribute to sig figs at all. It's only the value here, the coefficient on the scientific notation is what gives sig figs. So we have 3 sig figs here. So our answer should be rounded to 3 sig figs. So my answer is going to be 1,710 grams of caffeine.